Hello and welcome back. In this video we will look at the naive Bayes classifier, which is another supervised learning paradigm. So, all the slides are courtesy of Intel software and we will be using them as such. So, we will start off with some probability basics. Some of these would have been covered in some of the previous videos, but just for the sake of some continuity. So, we use Venn diagrams to denote the space of events x. So, the probability of event x is given by p of x, which is the circle highlighted in yellow, and we have another event y, which is again given by the Venn diagram circle right here, and again highlighted in yellow. So, we have two events x and y. The joint probability of their occurrence is denoted by p of x comma y, and of course, the single event probabilities are p of x and p of y respectively. Again here in the Venn diagram it is the region of intersection. The conditional probability again is given p of x given y is basically the region here. If you go back and you see that it is the parts of x that are also in y. So, that denotes the conditional probability p of x given y. What is the probability that event x occurs given that y has occurred? Similarly, we can define conditional probability p of y given x. Okay. So, the joint and conditional probabilities are related to each other. So, the joint probability p of x comma y is the conditional probability p of y given x times p of x, or equivalently p of x given y times p of y. This relationship you should have seen before. So, given this rule, we can then equate p of y given x times p of x is the same as p of x given y times p of y. So, that is the joint conditional conditional and how the conditional and joint probabilities are related. Okay. So, if you invert the probabilities, so if you can make use of this relationship right here, and if you can bring the p of x to the numerator on the denominator on the right hand side. So, we get this relation is p of y given x, the conditional probability of y given x in terms of conditional probability x given y and the individual probabilities x and y. Okay. Similarly, then the denominator p of x can also be derived from by marginalizing the joint probability over some event z. Okay. So, p of x is summation over z, summation over the joint the event z, p of x joint probability of p of x comma z, or also be written as conditional probability p of x given z times p of z, and of course, we marginalize over z, which is like summation over z. Here we have to you can choose z such that they are we can choose z in terms of mutually exclusive possibilities. So, for instance, if you are looking at treatment a diagnostic test, we can say z is the event that test is positive and test is negative. Okay. So, two options in z, test is positive and test is negative, and x is basically the, if you can think of x as the event that you have the disease. Okay. So, that way you can make a intelligent choice of z and you can marginalize over z to get the probability p of x in the denominator. Okay. So, this relationship that we have seen so far is the Bayes theorem, which you should have been introduced to, where the conditional probability p of y given x is written in terms of p of x given y and the individual probabilities p of y and x. Okay. So, this is this can be interpreted in the context of if you are supervised, unsupervised learning or supervised learning. This specifically in supervised learning, this p of y given x is referred to as the posterior probability, p of x given y is the likelihood, p of y is the prior, and the denominator is known as the evidence. Okay. So, typically this is the one that is very difficult to calculate, because we see that it involves summation over marginalizing over another variable, that typically turns out to be an intractable calculation in most cases. Okay. So, there are ways of avoiding this, and that is what we will see later on, at least for the naive Bayes we will see why we can avoid this. Okay. So, in the context of whatever we have seen so far, I think I might have mentioned when we talked about probability distribution the idea of likelihood. Okay. So, where we calculate the likelihood of obtaining data. Okay. That is exactly here right there. Okay. And later on when we looked at, when we get to look at map, maximum a posteriori or Bayesian regression, we will once again revisit these concepts. Okay. So, like I mentioned earlier, calculating this denominator is the difficult task, and most often than not we try to not calculate it, and in fact we will just ignore it as some constant in most problems, and so this whatever you calculate as posterior, it won't exactly be a probability, you might have to normalize, it is not normalized. So, this is the difficult thing to calculate, and we try to get over this calculation in most problems that we encounter. Okay. So, what we do now is we will, in the context of learning, supervised learning, classification, we will write the Bayes rule and see how we can be used for classifying. So, the naive Bayes classifier, that is where it draws its name from. So, we replace y with the class label C. Okay, we replace y with the class label C, and of course, this is again Bayes rule for that. For that class, of course, like I mentioned earlier, we are not calculating the evidence in this case, because it will involve a sum which is difficult to calculate. Okay. So, the p of y is p of x is something we are not taking into account here, we will see later, because we see that what you have done here is we have tried to calculate p of c given x. So, the probability of the class given x. So, the class is basically if you have a classification problem, it could be multi-class or binary class problems. Feature is basically your input data points, training data. So, the probability of class given x is basically your classification, right, that is we are trying to classify the classify based on input feature x. So, what we are so this p of c given x. So, if you have 3 classes, we can write 3 such expressions. So, C1, C2 and C3, and in each of them the denominator is going to be the same, p of x is going to be the same. So, when you are comparing them, the score, the output p of c given x up to a same multiplicative constants, we can compare them. So, we do not actually have to explicitly calculate p of x, right. So, given this, based on Bayes rule, we have this expression p of c given x is p of x given c times p of c. We are ignoring p of x because it is the same for all classes. Right. So, what the idea is, we have to calculate, so you evaluate this for p of C1, C2, let us say 2 class problem, and we just compare these 2 numbers. So, of course, since we are not normalized by p of x, it will not exactly be a probability value, we can call this a score. We compare the scores we get, and whichever is the higher score, we assign it to that class, the input data point to that class. Okay. So, how do we actually go about doing that, right? So, let us just look at the calculation. So, we want to calculate p of c given x. Okay. So, x is not in this case, it is not one variable, one dimensional, right, it is n dimensional. Okay. N dimensional. So, which means that there are n features. Okay. So, we can explicitly write down this p of x, this is what is written as explicitly here, p of x1 to xn given c times p of c, and then we apply Bayes the chain rule of probability to this particular expression p of x1 to xn given c, which then we can write it in this form. So, p of, so if you look at it, it is x1 to xn, we have taken x1 as individual variable and then group these as one variable, x2 to xn as one variable. So, then we can once again use the Bayes rule to rewrite this as p of x1 to we can use the joint probability, how we write the joint probability in terms of conditional probabilities. We can use that rule to write down this p of x1 to xn given c as p of x1 given x2 to xn and c times p of x2 to xn given c. Okay. So, which is the way we write, how we learn to write the joint probability in terms of the conditional probability. Now, if you recall, I will use a and b instead of x and y, just to, we wrote p of a given b as p of a and b, given p of a given b times p of b. That is exactly what we did here, but then there is a conditional probability here, which is conditioned on c, the class, and of course, we have taken that into account when we wrote it out. Okay. So, this so if we can do this successfully, right. So, we have done this for x1, now x1 is here, again we will take this and we can write it as p of x2 given x3 to xn comma c times p of x3 to xn given c. We can write this expression like that, right. So, we can keep writing this way and decompose it. So, but the problem is doing this calculation is hard, because then we have to do so many terms. If we have 100 features, we will have to expand, and then we have to calculate this probability conditioned on calculate the probability of one feature conditioned on the others, right. So, this is hard. So, then what we do is to make this so called naive Bayes approximation, which says that all the features are independent of each other. So, if we go back, so if we look at this, let us just write down this term here, p of x1 x given x2 to xn and c. So, then what happens is p of x1 given x2 up to xn and c. Okay. Since we assume that all features are independent of each other, then this is the same as p of x1 given c. Okay. Because it does not depend on x2 to x1. So, this is the naive Bayes approximation, or the assumption, if you can call it. This is an assumption because you will have seen in real data features are typically not independent. There is always some correlation or some kind of relationship between the features, but then we just ignore those, and then we independently calculate these quantities, okay, to get to the probability of a class given a feature x. Okay. So, so if we have a multi-class problem, we calculate this probability for each one of those classes and assign it to the largest class with the largest probability for a given new data point x. Okay. So, this can be written in product form like this. So, probability of C of the class, prior probability, this is called the prior probability of the class multiplied by I product of I equal to 1 to n p of x I given C. Okay. So, this comes about by making the assumption that all the features are independent of each other. So, that way the dependencies of one feature on the others goes away, and that is why we are able to write it in this simplified form. Okay. So, as I mentioned earlier, the way to do class assignment is what we call the map rule or the maximum a posteriori rule. Since we calculate for every class k, if there are capital K classes, we calculate this probability of C1 given x to probability of Ck given x, calculate. So, k numbers will be calculated, and the data point will be assigned to the class with the highest probability. So, that is the argmax there. Okay. This is the gist of the naive Bayes classifier. Okay. So, as I mentioned, select potential class with largest value. Okay. It is no longer a probability because we have not normalized by p of x. So, it is just some number, it is called a score. You evaluate the score and it is assigned to the class with the largest score. So, multiplying so many numbers, because in this case let us say we have 1000 features or 100,000 features, this can cause overflow problems, underflow problems, etc. Especially since you are multiplying with probabilities, it can cause underflow problems. So, then you just calculate the log of that. So, this is again another score that you can calculate. So, the product gets, if you take the log of this whole expression, then the product gets converted to a sum here. Okay. So, we can do that. So, let us see how we can look at, we have looked at this in the, I think we did the binary decision tree algorithm. So, we look at how to predicting tennis with naive Bayes, right. Remember, we have for a bunch of days, we have the following features: outlook, temperature, humidity and wind, and based on the output, temperature, humidity and wind, we decide whether to play tennis or not. So, it is a 0-1 problem. Okay. So, then let us see how we can use naive Bayes to deal with this. Okay. So, example, how do you train the naive Bayes classifier? Okay. So, the probability of play equal to S is 9 over 14, we have 14 data points. probability of play equal to no is 5 divided by 14. Okay. So, this is your P of C. If you remember from the previous slide, this is how we calculate the probability of the class, right. And we calculate the probability of that particular feature given the class, right. So, how do we do that? So, the outlook takes values sunny, overcast and rainy. Okay. So, if you go back and look at the counts, so out of the 9 times when we say play is yes, so given that the class is that we play we decide to play, twice it is sunny, 4 times it is overcast and 3 times it is rainy. So, that probability we can just calculate as a frequency, right. Similarly, out of the 5 times when we decide not to play, when the class is 0, 3 times it is sunny, 0 times it is overcast, 2 times it is rainy. We will see how to deal with this 0 later, but that is right for now. Okay. Similarly, we can do that for temperature. Now, for the 9 times we say we decide to play, twice it is hot, 4 times it is mild and 3 times it is cold. So, the probability is that. Okay. So, this is basically if you go back, I will show you the this we are calculating these numbers, probability of xi given Ck. So, what does it mean? Probability, this we are trying to calculate probability of temperature equal to hot when play equal to S, that is this column. Similarly, this column is probability of temperature equal to hot when play equal to no. It is not exactly the whole column, this is basically this particular row, that is what we are calculating. Similarly, the probability of temperature equal to mild when play equal to S is what we calculate here, and with probability of temperature equal to cool when play equal to S is what we calculate here. Similarly, so that is the so here the class is play equal to yes or no corresponds to C equal to 1, play equal to no corresponds to C equal to 0. Okay. And these are the xi's that we are talking about. Okay. So, we can calculate these tables for the based on the training data, right. So, we can calculate these conditional probability tables based on our training data. Similarly, for each classification C equal to 1, C equal to 0, we can look at humidity and say probability humidity equal to I given class C equal to 1 here, so on and so forth. Okay. So, the one good exercise is go back and see if you can do this calculation yourself. Okay. So, that is the way to do this calculation, right. So, similarly for wind is strong or weak. So, probability of wind equal to strong given play equal to S, which means here again corresponds to C equal to 1 and this corresponds to C equal to 0. Okay. So, these are the calculations that you have to do. So, what we do in naive Bayes model is we work with the given training data and estimate these conditional probabilities just by doing the frequency of occurrence. Okay. So, that is the only calculation that we do for the naive Bayes model. So, then what happens when new data point comes in? So, new data point is a new set of features. So, we have probability or we have x equal to outlook, we have to give outlook, temperature, humidity and wind, and we have to for this x outlook happens to be sunny, temperature happens to be cool, humidity happens to be high and wind equal to strong. Okay. So, then the way to calculate this probability, we want to calculate probability of class C equal to 1, C equal to 1 given x, sorry, this is basically probability of C equal to 1 given x, this is probability of C equal to 0 given x. Okay. So, how do we do this? We go back to the naive Bayes formulation. So, if you remember correctly, it is probability of C class of the class times the product of I equal to 1 to n probability of class given feature, that is our formula. This is the probability of C given x, this is what we did. So, the probability of C in this case, probability of C equal to 1 for the first row, probability of S, which is we calculated that as 9 over 14. If you remember, there are 9 data points which are, so here in this case when you do probabilities you just do the frequency, right, relative frequencies. So, out of the 14 data points 9 times you decide to play S. So, probability of S is 9 over 14, okay. And for each one of them, probability of sunny given that you play tennis, probability of cool when you given that it plays tennis, probability of high winds when you play tennis, probability of strong wind, and temperature is high, I think this is temperature. So, we can look all these numbers up from the tables that you calculated here, okay, and we just plug them back in there. Similarly, we can do the same thing for probability of not playing tennis. So, for instance, this is how the table outlines how we calculate it. So, for feature outlook equal to sunny, these are the conditional probabilities that you evaluate, and if you calculate it, okay, this is the overall label, this is, these are the P of x I given C, and this is P of C. You take the product of all of them, whichever comes up with the higher score, here in this case it is 0.0206 is higher than 0.00053. So, you decide that you will play, you will not play tennis, okay. So, we can we'll address the problem of what happens when you have a category with 0 in it, right. So, what does that mean? So, for instance, if we go back, I think there was one, remember this. So, what happens here? So, here probability of overcast given that play equal to no is 0. There are no incident, there are no events there in your data point, there are no, you do not have any data point with outlook is overcast and when you decide not to play, okay, you do not have that data point. So, then when you construct this empirical probability you get 0. So, what is the problem with that? Let us say instead of outlook being sunny I put outlook is overcast, especially here I put overcast, then I will be multiplying with the 0, one of these numbers is a 0, right, instead of this one will become a 0. So, then we get a 0 probability. So, that does not make sense, okay. So, one way, so we will go back here. So, the one way people address this, one way to address this is if you get any feature which has like a 0 probability or a frequency, you can just ignore that feature, okay, but that is like a very strong decision to make because it might be the very important feature, except that maybe you do not just have data points, right. So, there is something called Laplace smoothing, which is basically you add 1 to the numerator. So, you kind of increase the probability by assuming some uniform distribution, that is what you are doing. So, for instance, if this in this case let us say there are 2 features, that is what is here, and one of them feature has 0 frequency of occurrence, you have a 0 there, okay, and you have in this case P of x1 over C, instead of putting a 0 you just 1 over the count that you typically have in the denominator for that particular class plus n, okay. So, for each one of them you can do a similar thing. So, for instance, if since you have increased this artificially, okay, you can also do the same thing by for the other class, for the other features. So, for even for feature 2 where you actually have data where it is not 0, you have the count for x2 and C, basically this is the number of times that x2 happens when class is C, and then you increase that also by 1. So, this is a technique, it is called Laplace smoothing, wherein you artificially add to the numerator of that class, and that way you make sure that there are no 0 multiplications, okay. Go back and show this probability calculations for this particular data set, right. So, how do you calculate these probabilities, right. So, we saw that we will just walk through this. So, we are trying to calculate, if you go back and look at the naive Bayes formula, we are trying to calculate these numbers, probability of x given category. In this case, the example we looked at, the category is 1 or 0, 1 corresponds to S, 0 corresponds to no, okay. So, in this case we are trying to calculate probability of x, give a feature x, in this case feature is sunny. Actually let me rephrase that. So, we have to be really clear about how this works. So, we want to calculate the probability of the feature sunny, sorry, we have to, I am making the same mistake again. So, but it is okay, we will just calculate the probability of feature outlook. This is the feature, outlook is the feature, right, that is the name of a feature, and we wanted to take a particular value. Given that we decide to play, okay, given that class is 1, that is the probability that we want to calculate. So, the way to calculate that is we compute the number of times. So, before we do the new let us do the denominator first. So, we are looking at the category 1, class equal to 1. So, the number of times in the data set that class equal to 1 occurs is 9, right, and among all the data points for class equal to 1, how many times is outlook equal to sunny, right, that is 2. That is the that's how you calculate the probability here, okay, based on the training data. So, based on the training data, whether it is in this case this is categorical, right, this particular feature is categorical because it takes on 3 values, sunny, overcast and rainy, okay. Similarly, in fact, in this entire data set all of them are categorical, there is no actual continuous variable or anything, but that is how you would calculate it. So, for instance, let us go back. So, if you look how many times do we play, we decide to play, we say yes, category this is equal to 1, 2, 3, 4, 5, 6, 7, 8 and 9 times, okay. And out of these 2, out of these 9 we have outlook sunny twice if you look at it, okay. So, both times we decide to play, both 2 times when outlook is sunny we decide to play. So, that's why the probability of x given C in this case where outlook is sunny given play equal to S, that is what this corresponds to. So, this is 2 over 9, okay. So, this is what we have to calculate for every one of those variables for every class, right. So, the way to again look at it is if we have let us say 3 or 4 classes, then there will be 3-4 columns here, and for each one of those columns you have to calculate the probability of that particular feature occurring with that particular value, okay, and make that table. So, naive Bayes training basically involves making this probabilistic table. So, depending upon the variable and your training data, you will have to make the figure out a way to calculate the probability.